first question. Here is a table with the number of hours in labour expecting mums experienced at a hospital last month. What a poor woman. That poor woman there spent 24 hours in labour, but there's some with 30. So the first question they ask you is, what's the range of the data? Remember, that's the difference between the biggest and smallest number. So the smallest one I can see is 1 hour. And my site's not great. I think 30. Can anybody see bigger than 30?
32.
There's a 32. What row is it in?
Right below the 30.
Oh, God, yeah. Okay, so wouldn't the range, I'll just write down what the calculation is. Wouldn't the range be that? So you would just put in 31 hours. Nothing really. Well, I proved it wrong. There's nothing really difficult about that, but if you focus, you'll find the big one. Now, here's the next question. Which of the following is the best options for dividing the data? If you took that data and wanted to make a histogram, you wouldn't do how many had 1 hour, how many had 2, how many had 30, how many 31, 32. Wouldn't you have one this wide and the rectangles would be zeros and ones and maybe a couple of twos? So what you would do is you'd group the data. And they give us they give us 4 choices. For instance, you could do the groups in 6 hours, right? Like 1 to 7 and 7 to 13 and so on. Or you could do it in 2s and 4s and 10s. So I'm going to hit use salt button. Show you that guy. And there's all the data. The first person, 24, I guess. The 25th person was 25. And now I'm going to go to charts and graphs. And then I'm going to select. Now, do you see this bit here we haven't used before? Histogram setting. Right, the starting point is 1. Wasn't 1 hour the smallest number? So you put 1 there. And the choices that we got, although you can't see them, were starting at 1 and doing intervals of 2. So here's intervals of 2. Now, when I generate it, that's pretty good. Would you agree it's a pretty decent looking histogram? One of the choices was 8, I believe. Would you agree, although that's correct, would you also agree that there's not an awful lot of detail in that? You can't really see much of what's going on. So out of all the choices that work, I suggest, or I believe, that for that question, would you agree that's a pretty good choice? And you even get to see some numbers that are some groups of numbers that weren't even there. That particular histogram, I would say, has no shape. Would you agree there's no particular shape to it? It's not skewed left, skewed right, or symmetric. So does that question kind of now make sense? Because okay, where is it going? Here we go. So the width is 6. The one I chose was this one, the width of 2. If I'd done, 4 and 10, they too wouldn't do quite as good. You might say, why that one, I didn't even bother trying. Do you notice what's wrong with the first choice? I wouldn't even bother trying it on that diagram. What's wrong with it? Why groups of 6 starting at 6 hours is a bad idea?
Because it doesn't show the lowest variables.
That's it. That's all it was. So end of the day, there's your guy. Now, can you see this is a much bigger set of data? Isn't it good that we've got salt to work with? Now, it does say what's the range of data. So I'm just going to hit the salt button. And I'm going to go into charts and graphs, and I'm going to pick disease per tree. And let's see. There we go. The smallest number is, yeah, I finally found it, was 0. Can anybody scan through those numbers and tell me what the biggest one is? Right now I'm seeing, say again?
29.
Okay, so 29 take away 0 is 29. So that we had to do the hard way. And now we are going to fill in this fella, right? Now, what some of the features I'm going to look at. Do you see that these are groups of 5? Now, I could just do it behind, look at all those datas, and only include those 0s to 5. Now, you notice it's got that little less than to remind you that that only means 0 up to 4.9999. If you're a 5, you belong in the second group. But I should be able to get to do that for you. So let's see if I can. Select a variable. Okay. Groups of 5. Recalculate. Now, 0 to 5. Can you see when you put your mouse over it, it even tells you how many observations are there. But couldn't you tell just looking at the height? So that first one would have 9 in it. The next one would have 10. Then it's 9 and so on. Do you see that that guy there does all the good hard work for us by actually figuring out how much is in each group? So when we come to do that question, all we need to do is say, oh, there was 9 of them, and there was 10 of them, and there was 9 in that group. You see them all? And we're done. Now, it asks you for a histogram. Well, is it not the same histogram I had a few seconds ago? Now, looking at this one, is it uniform, bimodal? Oh, that's a good one. Skewed right or skewed left? What would you call that, roughly?
Roughly uniform.
I would. I'm like that. Bimodal. Has any? That's a term I've not used to describe a histogram. It's never came up, so kind of new to me. What do you think a bimodal distribution looks like? And the key here is in the word bi. Any ideas? It means two-hilled. So can you imagine a distribution that doesn't, not like a normal symmetric, bell shape, right? One of those guys. But it went up and down and then up for a second time and down. That would be called bimodal. If the data had 3 hills, it would be called trimobile, and so on and so forth. It's not really very common to describe things using that term, but they did in this case, so I guess it's fine. So far, so good. Just finishing off these questions here. Question 15. According to medical research who train other medical professions in advanced cardio support, ACLS, in the Western United States, the following have the given average life expectancy. Okay. Hawaii, 81.5. Montana, Oregon, and Washington. Oh. We're quite good, aren't we? So if you live in Washington, you're going to average life expectancy is about 79.7. I'd rather be in Hawaii, to be honest, but we're pretty good. Now, is this data about life expectancy? Oh God, I'm not going to insult you. Isn't that numerical? I mean, it's numbers. Now, use this stem and leaf plot. So it's been created. You see, this is a stem and leaf. Now, the stem is 77, 78, 79, 80, 81, and the leaves are these little guys here. Now, in this key, what number does that 6 there represent?
Tenths.
Tenths. And it would represent 77.6, right? Tenths. We all agree on that? Tenths. In a different set of data, couldn't that be units? Couldn't the 76 mean, or 77.6 mean 776? Couldn't it? You know, in a different context. So that's why you should always have a key. I know they haven't given a key, but if they had written a key here, I guess they didn't do it because it would make the answer even more easy. Wouldn't you do something like 7/6 means 77/6 means 77.6, right? You'd put that down to make it clear to everyone. Now it says determine whether that's true. I'm letting you do that one. And here is another guy that I'm going to do with you with a different set of data. Okay, so we are going to do another stem and leaf. This time it's with 2 different sets of data. So let's suppose we took a set of data and I'm making this up. We took the points that the Seahawks got in one of their seasons, and we looked against. Give me a team. Who's this? Anybody support a football team that's not Seahawks? Give me a name.
The Huskies, I guess.
Okay, well they are. That's true, but they're kind of in different leagues. We'll do the Chicago Bears. How about that? Right now, since I'm making up numbers, because I don't want to spend time going online and finding the real data, let's suppose we looked at the last 10 games or something, or whatever number, and the Seahawks got 15, 15, 17, 17, 19, 21, 23, put a 9 there, 31, 54. And the Chicago Bears got 20, 21, 23, 25, 27, 33. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2, 4, 6, 8, 10, 2, 4, 6, 7, 8, 9, 10. Okay, so here is the data. I've made my life a little bit easier, and I've put the data into order. So how do you do a stem and leaf where you want to show both sets of data on the same diagram, right? You don't want to do 2 stem and leaves, you want to do 1. In this particular stem and leaf, I'm going to start at 0, and then there's going to be, I'm making a little space here, 10s, 20s, 30s, 40s, and I'll finish with the 50s. And on one side, you put the Seahawks, and the other side, you put the Chicago Bears. Aren't the Chicago Bears probably the only team that's worse than us right now? Nobody knows. Okay. On this side, you put the data for the Seahawks, and on this side, you put the Chicago. Have you noticed I'm doing the single guy, not the double? So there's not 2 zeros, 2 1s, 2 2s, so on, right? So 9 for the Seahawks. 15, 15, 17, 17, 19. Do you notice how the smallest one is closest to the middle stem? And you grow out the way. Right, the 20s are coming up next. There's a 21 and a 23. Then there's a 31, and lastly, there's a 54. Are we good with that one? Right. Now let's look at the Chicago Bears. They start at the 20, so there's there, and then there's a 1, and then a 3, and a 5, and a 7. And then there's a 31, a 33, a 41, a 51, and a 55. Now, when you see them visually like this, I think it makes it a little bit easier to see the differences in the number of points that they get per game in this pretend story. Would you agree that the Chicago Bears are typically getting higher number of points per game than the Seahawks? That seems reasonable. I don't think I've gave you enough numbers to really make a decision about shape. There are just not enough numbers. But I guess if I was a kind of had to make a decision, if I turn this one on this side, would you say it's maybe skewed to the right? Roughly high and then getting lower, skewed to the right. You got to be careful with this one. If I turn it this way, you notice that the data happens to go backwards. Which one of the two skewed is this? Is it skewed right or skewed left? So you have to switch something in your brain. Is this skewed right or is this skewed left?
Skewed right.
It is skewed right. I hope it shines through here. Can you see if I turn it over, you can see when the data is from left to right, the way you should read it, right? Small to big. It is definitely going to the right. So if you get questions, and you will, is it skewed left or is it skewed right, or which one is bigger or better, or whatever the phrase they might use, that would be the one I would look at. Are we good? So that would be an example. If you were wondering how you would do data like that, but as box plots, you do your line. I won't do the details here, and then you would do, the 5-figure summary that you can get, and you would do the Seahawks, and the Seahawks might look something like this, and then you do the Chicago Bears, and they would look something like this, right? And you just do them one above the other using the same scale, and then you tell people who the Seahawks and who were the Bears. So that's how you would do it if you wanted to do it as bar charts. If you wanted to do it as dot plots, you just do one line, and I'm making no attempt even to be accurate here, right? You do the Seahawks, and then, well, I can give myself a lot of room here. You do another line just like it underneath it, and you then do the Chicago Bears. Right, so basically you just do two separate pictures. And for histograms, you do the same. Histogram is one at the top, and then straight under it, you draw the histogram of the other. So using the shapes that we're kind of used to, the graphs we're kind of used to, the stem and leaf is the only one really that combines as one big picture. Don't the others just look like you do the same thing twice? And so you don't really change much apart from that. And that is us. We have finished everything I want to do in that section. Are there any questions? No? Okay. Then we're now going to move on to the next bit. So this is not going to be in the test, and this is not going to be homework for this week, but it will be due next week. So here goes. Numerical summaries of quantitative data. So there are two types of numerical summaries. That are typically used in statistics. So these are the most common. First kind has a fancy name. It's called a measure of center. So you have a whole set of data, right? You collect the ages of every single student at OC, right? Like 6,000 numbers. And we could put it into a histogram and we could do a 5-figure summary on it, right? And we could build dot plots and stem and leaf and anything else, right? But that's all visual. A numerical summary is a single number that tells you something about all that data. And the ones that they call a measure of center are the ones that you probably would have said the mean of the data, right? You just add them all up and say the average age of students is 29 at OC, right? Or the average age is 31. And that one number is basically telling you the typical person's age at OC. And then you could go to some other community college in Texas and you might find that their average age is 40. Now that number tells me one thing. There's a lot more old people in Texas at college than there is here. You see how that one number may have came from 6,000 people, but it's reduced, it's condensed into one piece of information, the typical age of one person, right, or a person in that particular group. So measures of center are a good way of representing an entire group. And it also allows you to compare one group of data with some other different group of data, right? People at our community college and people in a Texas community college or whatever. And measures of center, there are three of them. The first one is called the mean. That's the one where you add them all up and divide by how many. That's actually the one that most people here call the average. But in statistics, we call it a mean. Now, the second one we've met before. Remember the 5-figure summary? Remember the guy in the middle? That's called the median. Right? We also sometimes call it Q2, don't we? If you want to. Now, the third one is almost not worth putting in, but I am putting it in for completeness. And the third one is called the mode. And the mode is the most common. Now, the only time I would think of the mode being actually a good number to represent the typical person would be if you've got a very small data set, like, 10 people, and you want to say what the typical person's age is, and 5 of them were 21. Wouldn't that be a good representation? Yeah, there's only 10 of them and half of them are 21. That will be the guy. Because if you calculated either of the other two, it probably wouldn't be 21. At least I could create data sets where that's not true. But don't focus on that one much because it's not that useful. It doesn't tend to give you a good idea. These two are very, very common. Medians and means. The government almost always tells you the median of the data. So let's let me put the second one in, then I'll come back to that. The second one is called a measure of spread. Now that is a number that essentially tells you how spread out the data is. Right? Could you imagine you had 2 classes and the average age was 23 in both classes? So you might say the mean was 23. Then you can't really tell much except that's the typical age. But can you imagine one of the classes, the ages were all over the place, right? There were some 12-year-olds and there was a 60-year-old, but they averaged out at that number. And then in the other class, everybody was 22, 23, or 24. Can you imagine that both those classes are quite significantly different in their distribution, how spread out they are? And so the measure of spread is a single number that tells you how spread out they are. If it's a big number, they're spread out all over the place. If it's a tiny number, they're all crunched together. Most of them anyway, are all crunched together. And they're always going to be crunched together, close to the measure of center. So there are 3 of them. One of them is called standard deviation. If you've done any chemistry, you've probably heard that term, have you? You ever seen it somewhere? Standard deviation? You might have. Okay. The second one you probably never heard of is called IQR. Actually, its full title, but nobody calls it that. It's interquartile range, but everybody calls it IQR. And the third one you've actually met. Haven't we today, at least once? Remember the one I got wrong because I couldn't figure out who the big guy is? The range is the difference between the biggest number and the smallest number. Right. And these two statistics tell you pretty much everything that you need to know. It summarizes all the ages of everybody in OC into just two values. So they're pretty good. So let's focus now on measure of spread. Measure of center. And as I said, forget about that one. That's just a red herring. Focus on those two because those are the important ones. A lot of data in science, in business, in medicine, when you want to say what the typical blood pressure of someone, an adult, is, or if you want to say the median life expectancy after treatment, you know, things that are single values that give you an idea of how good or effective a medication is, or how rich you are, or whatever it might be. You use these two. The government almost always uses median. So if you look up data, it'll say the median age of people in Washington State is 39, right? Or the median house price in Bremerton is 250,000, or, you know, they use the word median. So remember how that works is you take all the house prices in Bremerton, from the cheapest house you can think of to those bloody mansions, right? And you put them in order, and then you count along until you meet the middle guy, and you are the median, and that does it. On the other hand, the mean would be you'd add them all up and you divide. Now, you might think that both of those basically are doing the same job, but they are not quite equivalent. What do I get at here? One of the reasons the government uses median to represent the typical anything is because of outliers. The mean is badly affected by outliers. So I'm going to give you a pretend story to try and emphasize what's going on here. None of you know this because it isn't true, but Mark is one of Bill Gates' sons. He doesn't like to show off and tell people about it, so he changed his last name to disguise it. And I didn't know it either, but he's very honest, so Mark doesn't lie. And so I went and asked people in the class to tell me how much money they've got in their bank account, right? And round it off to the nearest thousand, okay? So if you've only got $22 in it, your answer is 0. And this is what came out. 3 of you had nothing worth talking about in the bank, right? To the nearest thousand. 1 of you had 1,000. 2 of you had 2,000. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you might think, well, what about Mark? Well, Mark was off that day. And so this is the class. This is what you all look like. So there are 10 of you, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's find out what the mean of this class is. And it doesn't take too long. That's hopefully. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 19, 29. 29 divided by 10, that comes out as what, 2.9. So won't that be $2,900? That's pretty good, right? Now, does anybody in this class have that number? No, but would you agree that 2,900 is about there? Typical amount. The next day, Mark turned up. And so it's the same data, but Mark has 200 million in the bank account because his dad's generous and he gave him a lot. So 200 million would be 200,000 thousands, right? So let's see what the result looks like now. It's 229,000 divided by 11. And the mean this time is $20,818,000. So the average amount of money, right? This class with Mark in it, doesn't it look like you're all millionaires, right? The average amount. Would you agree that that's not the typical amount of money that people in this class has? Isn't that darn outlier screwed up the information? Whenever you are calculating a measure of center, right, the typical person in your data group, be very, very careful, right? For those who are into old sci-fi series, danger, Will Robinson, danger. There is going to be a bad result. This number is not really going to represent what you think. So how do you think in practice we deal with still using the mean when Bill Gates people are in our data set? What do you think you do? How do you cope with it? Well, if you don't like it, you ignore it. You basically say, I am removing this outlier from my data because it is an outlier and it is distorting the true nature of the class. And in science, outliers can and are sometimes removed from the data set for this reason. Now, you're only allowed to remove it because it's an outlier. You're not allowed to remove it because it contradicts what you think is true. Right? So there's a big difference between that, right? Oh, well, I didn't like those 5 numbers because it shouldn't be that small. And I'm a scientist and I don't like those small numbers because it means my theory isn't working. So I'll just ignore them. That's called cheating, right? That's not doing it. But that is clearly an outlier, right? Now, let's go back to Bill Gates again. And this is the same class. And unfortunately, that comma, I'll just put it in as zeros in, right? There's Bill Gates. Now, there is 11 numbers in this data set. Let's find the median. Okay, when there's 11 numbers, how far along should I count to get the middle guy? Is he
5 or 6?
5 or 6? Let's see. 1, 2, 3, 4, 5 is here. 1, 2, 3, 4, 5 is here. Do you see that this one is right in the middle? So it's basically the 6th number. So if you have an odd number in your data set, like 11 numbers or 21 numbers, and you want to know how far along you should count to get to the middle, just add 1 to that and divide by 2. So call it 12 divided by 2, and that tells you to go to the 6th number. So would you agree that $2,000 is a much better representation of the typical amount of money people in this class have? Can you see why median is doesn't care about outliers, right? I don't even need to throw them out. Can't I keep them there? They're not doing any damage. Can you see why the government and I'm not a fan of governments, but I like that they do medians, because medians in many situations, especially when you know there's going to be outliers. Could you imagine that we tried to find the typical price of a house in this general area? Right, what a house sells for. can you imagine there's a couple of houses in Bremerton that are maybe 20, not Bremerton, Bainbridge Island, that are about 20, $30 million. Aren't there some really honking big mansions over there? Can you imagine what a 20 or a $30 million house would do to the average, right? The mean, if there's enough of them. Can you imagine those outliers would make people think that the typical house value in this area is that? Wouldn't it be a much better thing to say the median house value in this part of the world? And so that would be an example. So when you have a choice about which number you're going to use, if you believe that there's a good chance that there's some outliers and that they are big enough to make a significant difference, then it's better to use medians. It's just safer. Now, only for completeness sake, I don't like mode, but I really need to write it down once. In this question here, which of these numbers is the most common? Because that's what the mode is. Right. Would you agree, okay, it's not as bad as the mean, but would you agree it's quite random which one ends up being the most common number? Right, couldn't it just as easily have been a 3 if it had another 3 or a 2, or, well, it probably wouldn't be Bill Gates numbers, but you know, it doesn't reflect reality very well. But in a few very specialized cases, you might get away with it. But once we've shown you a couple of times, we just throw it away and you never see it again. So I'm quite happy with that. But you'll see it a couple of times and nobody ever talks about it. Any questions about that? Do you like the concept of mean, a mode, a median? So what I'm going to show you now is, got time? Yeah. This can be done sometimes in salt. And if there's a salt button and you hit it, I won't show you today, but I'll show you on Monday. We'll show you how salt can do this. You can imagine that if the data is big and it's all jumbled up, wouldn't it be very difficult to get the mode? Because when you have to, you know, put them in order first, right? And that would, God, it would be about this big. But if you want to, I'm going to show you how to do it on a calculator. And if you like what I'm doing, you can do it this way as well. Or you can just do it by hand if the data set is small. So let's put it on. And the first button you are going to press, so I'll try and take this slowly, is a button called the Start button. And that's here. And you see in that, you get a little menu. And the menu I'm going to use is number 1 called Edit. Okay. And I'll press Enter. And there's always a chance that there's some data from before. So just hit the delete button till it goes away. Now, once you hit Edit, you see these little columns, you put your numbers in. I could put these guys here, right? But I'm not going to. Just to show you one of the things. Let's suppose that they took the ages of people in a chess club or something. So there's a 13-year-old, then there's a 25-year-old, then there's a 46, then there's an 8-year-old, and a 47, and a 16, and a 13, and a 29, and another 29, and I'm just hitting random digits. But can you imagine you just type in the data one after the other and put Enter? Have you noticed that I haven't made any attempt to put it in order? Isn't that good? Because that would take you a long time if you had to. So that's like step 1. Get your data into the calculator. So it was, to remind you, Start button, number 1, Edit, and then just type it in. Right. So that's stage 1. Now I want to get the mean. I'd like to get the median as well, right? This thing doesn't do mode, but it does do the mean and the median. So what you now do is you hit Start button again. And I'm going to move over to Calculate. And right at the top, it has 1 var stats. You see that? That's where the mean and the mode and all the other stuff that I want is stored. So you hit Enter. And there's a flashing black cursor here, right? It's flashing on and off. The calculator's waiting for me to tell it where the numbers are. they're in a column that was called L1. And to get L1, it's blue button 1. Oops. Excuse me. What's up? It's okay, Billy. Sorry about that. My dog's got excited by something. They're pretty good guard dogs. Unfortunately, they bark at everything. So hopefully you didn't get too distracted. So 1 variable statistics, blue button 1. Now when I hit enter, everything I want is here. So the guy that we call a mean is X bar. So in this case, it was going to be 26. There's lots of other things here that you don't need to worry about right now. But if I hit the down button, can you see that the minimum was in 8, Q1, Q2, and there is the median. Hey, wasn't that quick? And that's how you can let your calculator do it. Now, you notice it has lots of stuff that we don't need to worry about. For instance, isn't that called the 5-figure summary? Do you see you get the 5-figure summary for that data right at the bottom? And you get all sorts of other things. So if the data set is reasonably small, you can calculate mean, mode, and median pretty much using the calculator. And it's pretty quick. Are we good? Just one last quick topic. If the mean is roughly the same size as the median, right? So in this case, would you agree 25 and 26 are pretty much the same? Can you not assume then that there are no outliers? Because if there was an outlier, there's a good chance that this would get distorted and be quite different from that, right? Secondly, because they are both the same, you can make an assumption that a lot of the time is correct, and that is that the data is probably, not guaranteed, but probably symmetric. That's good. If there are no outliers, and we're making this assumption now that there's no outliers, if the mean is a bigger number than the median, and if the mean, the other situation, is a smaller number than the median, then one of these two is a skewed left and one of these two is a skewed right. Okay. So if the mean is bigger than the median, what do you think it is? And you're really guessing here because you probably never heard of this. But if the mean is bigger than the median, any guesses? Any gamblers amongst us? So it's probably. None of you are willing to be wrong. You have a 50-50 chance of being right.
Okay, if the mean's bigger than the median, I'm gonna say it's skewed to the right.
In which case the other one has to be skewed to the left. And you are correct. What was your gut feeling? Or did you have a gut feeling you were just guessing?
I mean, I just tried visualizing it in my head because if the mean's bigger than the median, that implies that more of the data is on the
tail is on the right. Agreed? Yeah, I'm just putting words in what you're trying to visualize. Yeah. And that's exactly true. Now, we're making a big assumption here, and that is one, there are no outliers. Can the outliers screw this statement up totally? So if there are no outliers, this is true. It's not always true, because couldn't you just have some really weird random data with no shape to it, and the mean would be bigger than the median in that case? But if, in general, data tends to be pretty unrandom, right? There tends to be a pattern in data, unless you're doing something like the last digit of your social security number or whatever. And that might be just all over the place. But in most cases, there is a thing. Say your last name, everybody. Have a nice weekend. And I will see you again on Monday. Remember, your test is in WebAssign, and you can start doing it anytime you like. But I would make sure that you've done all the homework first, so you're ready for it. Bye-bye.